Welcome to Architect Tech Talk. These talks delve into the technical aspects of the Hazelcast platform, focusing on specific use cases. We chat with architects who work directly with customers, discussing how the platform has been implemented. This week, we talk with Randy May and Terry Walters about fraud detection in financial services. First, Randy will walk through fraud detection architectures, and then Terry will walk us through some of the requirements and technical aspects of how Hazelcast platform was implemented at a global financial institution.
My name is Randy May. I am an architect here at Hazelcast, and my background is all in consulting and working with customers who have kind of high velocity data problems that they solve with Hazelcast or similar products. And I've been in that space for close to 20 years. And our guest here today is Terry Walters, and I just wanted to say a couple things about him, then I'll let him introduce himself. But Terry is actually one of Hazelcast's oldest customers. And as well, he's sort of the mastermind behind a fraud detection system in a global card processing institution that you would all recognize the name of if we could say it. So anyway, that's why he's here. He's going to add a lot of value in terms and know-how in terms of fraud detection. And that's Terry. So Terry, say hi.
Howdy, howdy. My name is Terry Walters. I was a customer back in 2010, very early adopter of Hazelcast, and I've been at Hazelcast for almost a decade now. And I've given speaks at user groups, and I really enjoy helping users with web scale and things of that nature. And my specialty in the past decade has been top financial institutes, primarily around payment systems where it's got to be right. It's got to be fast. It's got to be low latency, and it's got to be predictable at scale.
Awesome. So we're going to focus in on a particular system just because it's easier to talk about one system. But one thing I wanted to point out at this stage is that fraud detection is used all over financial services. So there's, of course, card processing when you swipe a card, SWIFT transaction surveillance, mobile banking. There are regulatory requirements to do surveillance to detect money laundering. There's know your customer, and the list goes on and on. And these systems are generally global scale systems. So some of the biggest systems out there and some of the biggest challenges out there as well. So let's have a quick look at kind of a canonical fraud detection model, just to talk about some of the challenges and how this works. So basically, and I would say more and more customers are turning to, our big financial institutions are turning to ML to do their fraud detection, but there's also a place for rules. But regardless, what's constant is all the information you need to make the decision is not on the event, right? So if we're talking about a credit card swipe, it's not on the credit card. So in that case, what we have to do is if it's ML, then all those inputs we call features, right? So in that case, what we have to do is we have to gather up from disparate sources the most current information that we can and provide that as input or features to the model. And then we have to score it and make a decision, and then that decision results in an action. In the case of credit cards, it's a accept or a decline and so forth. So obviously we want the most up-to-date data that we can possibly get. We want to get it fast. And again, because of the increasing use of ML, what we need to be able to basically run ML at scale. We need to be able to parallelize it. So some of the key challenges here are data volume and velocity. So as models get more sophisticated, the amount of input data that they need is also growing up, or is also going up. And I think Terry can tell us some of the kind of specific numbers related to the systems that he's worked on. What are some of the typical data velocities and latencies that we're looking at here?
Oh yeah, it is absolutely some of the the fastest I got credit there for a while for maybe about 5 years. I ran as a customer. I had the largest and the fastest Hazelcast cluster, and I got knocked off that when I got assigned to a certain customer, this very large financial institute. And I was so excited to work with these people. They're just top notch, and their requirements are nuts. And for example, 50 milliseconds, like 50. That's their entire SLA. Now that's not the whole time down to where the point of sale happens, right? That's the time that the bank has to respond. That's it. Okay. So yeah, they literally have a 50 millisecond SLA. That's total. So their average response time in this case is right around very close to wire speed at 3 milliseconds. That is very, very fast, obviously, and their frequency is about 35,000 transactions per second per site, and they have many sites, obviously. But yeah,
Wow.
what would you like to know?
No,
How much does this cost? I mean, what?
Yeah, no, that's great. I just wanted
we literally saved them hundreds of millions of dollars, and they went public with that years ago. But we literally saved them hundreds of millions of dollars in anti-fraud because we were so much faster and so much more accurate than the competition. But yeah, it's about 35,000 TPS. During the Cyber Mondays and the peak times. And yeah, what would you like to know?
Well, I think that's it for this. I would just want to get a sense of scale here, so that people can understand the times and the times involved. I'm going to just pop back here. I'm not sure what happened there. Okay, yeah, and then I just want to point out there's always a trade-off, and this is why timeliness is so important. Obviously, you want to get your features need to be up to date. Or you could miss out on important activity that would have been input to your decisions. So that's important, but also the time window, right? Terry said there's a 50 millisecond time window. So the more complex algorithms and the more algorithms we can run in that time window, the better decision we're going to get. And so there's always this trade-off between you got to fit in that window and you want to make the best decision you can. And you don't want false positives to the extent that you can avoid them, because those are bad customer experiences. And then lastly, the system has to be not only fast, but you have to be able to update update your models and the inputs to the models, because fraud changes, right? Fraudsters think of new things, and fraud changes. So here is sort of a canonical blueprint of how we go about implementing a fraud detection system using Hazelcast. Now, there's an earlier video where we introduced the platform and the capabilities, but one of the capabilities that is in Hazelcast that a lot of people don't know about is a full event processing pipeline, and it's ideal for this. So pipelines are, you could think of it as putting together an event processor like Flink and an in-memory data grid like Redis, or name your data grid. So they're combined and co-located in a smart way, which means that we can actually process events we could process a card swipe on the node where the relevant data actually is. It's very fast. Okay, so but just to walk through this diagram a little bit.
Well, if I may interject, and I'm sorry, Randy, but that becomes very critical to be predictable at scale. It's one thing to be fast in this one moment. It's another thing to be fast at scale as you start scaling out, as the business grows and demand comes in. And, so to your point, you have to be able to make sure that you do the calculation where the data is and be able to have data affinity so that, it becomes predictable. So, that's very important. It's so easy to overlook,
right.
When you're on this level here, that's one thing. But these big financial institutes, they melt servers.
Yeah, and And if you're talking about two different products, how you can't get that, right?
Yeah. Yeah.
So anyway, so just to kind of paint the picture here, we use an event processing pipeline to accumulate all the features and keep them up to date. So if you need to calculate, let's say, all the dollars authorized in the last minute, which, believe it or not, is an important thing to know, then then basically every single authorization that comes in, that needs to be reflected in a feature somewhere. And so that's what these pipelines do. And the whole feature set can be saved in a Hazelcast map, which is in memory, key value store, distributed, fault tolerant, reliable. And then we can have another pipeline that's responsible for processing the card swipe. So dealing with formatting, retrieve the features out of the map. And we actually have an embedded ML inference runner that it'll actually run Python instances for you and submit the and get the score. There must be some default timing on this thing. It just keeps advancing. Yeah, so built-in ML inference, Python ML inference. And of course, if you're doing it in Java, like say with Onyx, that's also completely feasible as well. So anyway, that's kind of the canonical architecture for fraud detection. We're going to get in just a minute here. We're going to get into some variants as well that we're going to talk to Terry about. But so just to do a quick recap, this architecture with the co-location that Terry was talking about is very essential. And the ability to process these events, the events that affect the features instantaneously. Basically, that's going to result in your features being the most up to date, which results in better decisions. And the other aspect that I kind of keep mentioning is that time window. So this is just a nominal. Say you had 100 milliseconds. So spending half of that time doing plumbing leaves that much less time to do the actual decision making part. So by having this co-located architecture, which is really the key, it's allowing you to basically spend the most amount of time to making the business decision, basically running the best models. So that's kind of why financial institutions like to use Hazelcast. Just gonna leave that up. I don't understand why this keeps doing this. I know you'll have to cut this out. But anyway, so I did want to have a discussion after this, because this is just a high level blueprint, but Terry has some nuts and bolts. And one thing I wanted to call out is that so this is kind of a push model of calculating features, right? Like, every time an event comes in that affects a feature, it's kind of accumulated into that feature. That doesn't always make sense. And in fact, that's not what every customer does. Sometimes the features are actually going to be computed on demand, and sometimes they even have to be computed on demand because the answer depends on when you ask. So anyway, so Terry, can you tell us a little bit about how you can accomplish that? What are some of the alternatives that you see to this?
Oh, certainly. So, banks are like the government. They are a prime target for whether it's bots or spider, whether it's automated or whether it's actual humans trying to crack the system and all. At the end of the day, they have some of the wildest requirements. These people are under heavy regulation from the government. They're depending on which country they're in, of course, they may or may not be able to put that data over there, right? But the point here is that they have to change the order that the rules are run in. They change which anti-fraud rules are being executed at runtime. So this is not just, oh yeah, let's code it up and let it run. No. This is a very dynamic system. They even have, lazy always wins, right? So by co-locating the data, you definitely, be able to. I can't go into too many details, but let me say the largest retailer in the world is the customer of one of the largest financial institutes of the world. So you don't treat their data like Terry's data, right? So when Terry buys something, it comes up in Atlanta or whatever, right? And it looks at the dev caps, the device capabilities, and says, okay, I see Terry's phone is in Atlanta. I see this transaction's in Atlanta. No problem. It's in Terry's behavior. No problem. We'll approve that. But we've all seen where, it says, is this you? Right? Well, that's because the fraud system is looking at your past behavior, it's looking at your location, it's looking at all these, literally thousands of different data points. And to your point earlier, these are not idempotent calls. These are not, oh, we're going to give you everything you need to go do your job. No. We have to calculate it on the fly. But yeah, so they do have some of the, I've worked in several industries, and the financial industry, they have some of the most demanding. But yeah, it really comes down to being able to change at in that moment of time. That's what it really comes down to, being able to, at that moment in time. And you even said this earlier, sometimes you got to see, well, how much has this account been used in the past minute? Is this a bot? Is this bot literally pow, 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 pow? And it's like, well, wait a second. We approved this much already, and now you're asking for that much more. No, right? So right. It's that behavior, and that behavior has got to be very dynamic. So
right. Yes, absolutely. Yeah. The automated buyers or bots is is a really fascinating one, because now things like how many dollars are authorized in the last 5 seconds actually matter, right? It's not that a person is going and swiping their credit card, but a bot could be. So okay, this is awesome.
It's just dangerous. It's crazy.
Yeah, absolutely. So okay, so just to wrap up, could you tell us a little bit about why, at the end of the day, why was Hazelcast chosen for this one particular fraud system that you worked on?
Certainly. We were definitely involved in a rather highly technical and highly laborious bake-off with top contenders, of course. And ultimately, we won not because of Happy Path. When everything works, everybody looks the same on paper. We won when they started doing, Netflix is probably one of the first companies that kind of threw out the idea of chaos monkey, right? Just start killing stuff. Just start breaking
things. Right.
And they took that to heart. And when they started doing that, that's when Hazelcast started shining. It's like, wait a second. You have split brain protection. And we're not going to talk about split brain right now, but my point is, you have protection for when the network breaks, when we had this, and now we have this, and you now know who to trust. What? Anyways, and it really comes down to, banks have to not just be fast and be dynamic and all this wonderful, things that would drive a person mad. They also have to be highly, accurate. Consistent is the word I'm looking for. CAP, right? Being available. So having an AP system, it looks pretty standard across the board. But Hazelcast, after failing the Jepson report a decade ago, I was there, I remember, we hired up some very smart people right out of universities, and now we have the most, absolutely the best implementation of the Raft algorithm with respect to a CP subsystem, and the proof's in the pudding. I mean, we didn't grow this product out of the air. We grew this product by demand of the top financial customers. Does that answer?
Awesome. Yes, it does. Thank you very much. I think that's a wrap.